Okay, so last time we learned about the CNNs and its performance and why it performs well. I lectured that and explain a bit about the importance of the differentiability. So okay. So this characteristic is very important when constituting the deep learning architecture. So roughly, you can think you can differentiate some layers, then it is roughly equivalent to you can learn that layers. Okay. So I mean, you can think these layers, the deep layers, deep architecture as the baby who just born. Okay, he don't know about the world, right? So he can only cry. Okay, nothing. He can. I mean, she or he cannot do anything but cry because they don't know how to do actually. When deep architectures are first made, the situation is similar. Okay, their parameters, we will call that parameters as sector. Okay, they are randomly initialized. So if we input some images or other signals to this layer, then their output is some random value. Okay. So it totally doesn't work. Okay. When we first made this deep architecture, we first initialized this architecture, then this deep architecture's output some random value for the input. But we have to learn these deep architectures. We have to teach these architectures to have some knowledge about our data. Okay? So we have to, when this is denoted as X, and when semantic labels, if they are denoted as Y, then we have to have a lot of X and Y pairs. Okay? We need n number of, normally it's million scale data we need for training the deep architectures. So we need this amount of data to teach these deep architectures. Okay. So we somehow, when it's similar to teaching baby. So we input this X1 input to the deep learning architecture and say that you need to output Y1 for input X1, right? And for input X2, we teach these deep layers to output Y2, okay? And then after this process, this is called as learning process, okay? The deep architecture actually learn the data, okay? And after this learning step, the deep architecture, their parameter sector is updated, okay? And after that, given learned parameter sector, when we input new data X to the deep architecture, then it will output proper output, okay? So that is actually the basics of the machine learning, okay? Okay, so, but we can teach these deep architectures when they are differentiable. Okay. So because of that, this differentiability is important. You can think like that. Okay. Roughly, we can say differentiability of each layer is equivalent to the fact that we can teach each layer. Okay, we can update each parameter sector when they are differentiable. So that is mathematically explained in this slide. So this I is the input image. And we have to output some output here. We will call our output as Y, and our input is image, so we will call that as I. And this is some intermediate output X. So our functions would be like this. So initially, we will input our input image to function H, and that will actually output a large X. And also we will input large X to layer F, which have parameter sector. Layer H is not having any parameter, so we will not use any parameter notation here, but F is the function that has the parameter sector, so we can say it like this. And we have to output the final output Y, okay? And we can say this in one formula like this. Y is equal to like this. Is that true? Okay, so that is actually denoted here, right? And then, I mean, here you can see the text loss, right? Loss is the distance between the ground truth and our prediction. Okay, ground truth is in Korean is 정답. Okay, 정답과 추정치 간의 거리라는 게 손실 로스예요. Loss is the distance between ground truth and the prediction. Okay, so this layer is used during only the training stage. Okay. And yeah, these loss functions are required for training the network. And after training, we only use this part. Okay. And this is the, the differentiation, right? I said you roughly differentiability is equivalent to learnability. Okay, so these two layers, H and F, they are constituting the overall deep architectures. Okay, so we need to train. We have to teach these deep architectures to learn about the data. Okay. For that, we need to secure each layer of these deep architectures are differentiable. And for that, we need to check each layer is meeting this condition. And what they are saying is dy dx. So for individual layers, for F, their output Y need to be differentiable with respect to their input X. That is this. Okay. So for given layer, their output should be differentiable with respect to their input. That's dy dx, right? The next term is dy d-sector. Next term is dy d-sector. Sorry. This means your output should be differentiable with respect to their layers parameter sector. Okay. So we need to calculate these two gradient, the differentiation values. for each layer. Okay. I mean, this is because we have to calculate these values. So I mentioned, I already tell you that this parameter sector is the one that needs to be updated during the training, right? And this sector is updated to the new parameter by adding some value, right? So this is the old parameter sector, and this is the new parameter sector, okay? You will update old parameter sector by adding some values. And if you see that, you can see this is, you can already know that this is equivalent to DLD sector, right? And L here is meaning the loss, okay? And this is actually the direction. I mean, this is actually measuring the amount of change. I mean, the change of the L when the this physically this term is measuring the amount of change of L respect to the change of sector. Okay, so actually this is measuring the how much L changes as sector varied. Okay. So I mean, we need to minimize the loss L. Okay, loss. Loss is the distance between the ground truth and the prediction of this network. Okay, at the initial stage, this network doesn't know anything. So their prediction, the Y value is totally random. Okay, so the loss, the ground truth is the 정답. So this is correct value. So this is constant. So only the changed value is the prediction Y. Okay, we had to update the parameter sector to make Y close to their ground truth. Okay, and loss is measuring the distance between ground truth and prediction. So when prediction goes close to ground truth, the loss value, it is decreased. Okay. So our aim is actually during the training, our aim is to minimize the loss function. Okay. And this physical value, DLD sector, is actually let us know where to go, where to update parameter sector to minimize the loss area. Okay, are you following this? Okay, and this epsilon is very small constant, like this one. Okay, so this value, actually this is denoting the direction where to update parameter sector. Okay, and we multiply very small value on that direction and update parameter sector. And that is actually the new parameter sector. Okay. Are you following this? This is very important actually. So this is actually the rule to update the parameter sector. Okay. And to know this value, these two gradient values are required for every layers inside the network. Okay. So as you see, this is the chain rule. Is there anybody who is not familiar to chain rule? Maybe not. Okay. So by multiplying these two terms, the new term, the gradient, can be obtained, right? So this is actually the dl dy. dl dy is the differentiation of these laws respect to this y. So for this layer G, this is saying the dl dy is saying differentiation of the output of this layer G respect to their input, and dy dissector is meaning the differentiate for this layer F, the differentiation of the output Y respect to their parameter sector. Okay, and for obtaining DL sector, we have to somehow merging these two. You can think these two layers, layer G and F, are merged, and DL sector, this is the differentiation of these layers, bigger layers output respect to their parameter sector. Okay, so for individual layers, if you know these two terms, then you can calculate all the layers, all the bigger layers, these two terms. And eventually you can calculate this DL sector for every layers. Okay, so it happens thanks to the chain rule. Okay, so by this kind of characteristic, you can multiply individual layers gradient to get bigger layers gradient. And by doing that, you can calculate all the layers DL sector, and after getting DL sector for all the layers, the thing you have to do is update all parameters using this rule. Okay, then this deep network gradually know about the data. Okay, when babies are born, just born, they don't know about the world, but they, by getting some feedback from their parent, they can know about the world gradually. Okay, this process is similar to that. Okay, everybody clear about this? Okay. So this is again denoting that. So this is the loss function, and this is the hi, and these three function g, h is the layer denoted here. Okay, and when inputting this I and using parameter sector, you can represent the loss function as the function of the parameter sector. And this is the rule to update the parameters from the old parameter. Sometimes we use this symbol old here. You will get the new parameter here by adding this DL sector and multiplying some small constant to that direction. We will update the parameter sector. Okay. And this epsilon, which is the small constant, is called as the learning rate. Okay, maybe I will I will teach this in the subsequent lectures. Okay, you have to properly tune this learning rate to make this work. Okay. Anyways, this is the the rough picture for the deep learning. Okay, if you properly understand this process, the loss and DL sector and this updating rule, I can definitely say you understand everything about the deep learning, right? But you also have to learn more about the characteristic of other learning rate and other method to update this sector and others. But that's kind of supplementary. But the core of deep learning is, I think, this formula. Okay. 혹시 에어컨 꺼져 있나요? 이렇게 덥지? 보기만 알겠습니다. And actually, when calculating this kind of gradient, you may learn that in the high school or the freshman of the university, you may learn that if you, for example, differentiate this kind of formula, you may do it like this, okay? Maybe calculating the closed form solution for the function, you will calculate the gradient value, okay? But this is the way to calculate the gradient for humans. But when implementing the this calculation of the gradient in PC, in computer, I mean, this kind of method is used. So somehow inside the language, the program, we build some of the graph like this. So this function is denoting this kind of function. Okay, so x and y are plussed, and they are multiplied with z to obtain the f. This is the function defined here. Is that true? Right? And we assigned this -2 and y, assign 5 to y and assign -4 to z. Okay, so we can calculate somehow this intermediate value becomes 3 when adding these two, and we multiply these two, then it becomes -12. Okay, that's very easy. So normally we call the process from left to right as the forward process. And here I already defined it as the forward rule. So this, how to obtain the output from the input, that is called as the forward rule. Okay, and this is called as the backward rule. The differentiation of the output respect to their input is called as backward rule. And this dy d theta, which is the differentiation of the output respect to their parameter, is called as parameter update rule. Okay. So calculating the forward process, that is very intuitive. You can just calculate their values, but I will show you how to calculate the backward. I mean, we have to calculate df dx, df dy, and df dz. Okay, this is not very simple. Okay, but I will show you how to do that. So I will first define this. When calculating this, it have to be happen from right to left direction. And I will first write it like this. And we have to actually calculate it like this. Okay. So actually, and another thing is, we have to first calculate the last term, df is always the differentiation of itself respect to itself is 1. So we will call the differentiation of the gradient value here as 1. And then here we have to calculate df dq first, okay? And df dq is actually defined as this. So I mean, when calculating df dq, you have to regard this g as the constant, okay? And then you can differentiate this differentiate this equation by q. Okay, so the left term becomes df dq, and this is the only variables, and this is the constant. So you can get the z here. Okay, and here the z value is actually -4. Okay, z value, this is also the constant to this q. So this is g, but g is set as -4. So this value becomes -4. Okay. You get this? And here we have to calculate this value. And when calculating df dz, we have to regard this q as the constant. Okay. And so we differentiate these two terms respect to z, and the left term becomes df dz, and this becomes q, but q is again constant to the variable z. So that is set as 3, so this becomes 3. Okay. And again, I mean, we get these two gradient value, but actually we have to calculate this. Okay. And then what we do is we also write down these next layers forward rule here. Okay. And by the chain rule, actually, df dx can be obtained from this multiplication. We already get this here. Okay. We already get this here, but from here to get this, we need this term. Okay. And we can get the remaining dq dx from this by differentiating this formula. So we can differentiate the both sides respect to dx, and we can regard this y as constant. And if this is the only variable, so we can differentiate x respect to x, and that becomes 1. Okay. And this is, we have to calculate this, but this is already get as -4 here. And this is 1, we just calculate. So if we multiply these two terms, then it becomes -4. Are you guys following this? And also here, we have to get this df dy, and this is df dq obtained by multiplying these two terms. We already get this from the previous layer, and this is -4, and we have to calculate this remaining term by differentiating this equation. And we can differentiate this equation by differentiating both terms respect to y. So the left becomes this, and we can regard x as constant and this as variable. So constant becomes 0 when differentiated, and this becomes 1. Okay, so this was -4, and this was calculated as 1. So their multiplication is -4. So df dy, that becomes -4. Okay. Are you guys following this? So this is initialized as 1, and we calculate this as -4, and this is -4 multiplied 1, so this becomes df dx, this becomes -4 multiplied 1, so it becomes -4, and df dy, that is also -4. So this one becomes like this. So I recommend you to practice this by rewatching the video. So maybe after this class, I will upload the video into YouTube. Okay, maybe including the previous lectures video. I will let you know where to go. And because I always raise this calculation of gradient as the quiz one. So I encourage you to study this. Okay. Okay. So actually, this is this is the backpropagation algorithm. So maybe when learning the deep learning, you have heard about this backpropagation. Okay. This is actually how the backpropagation works. We always have to get this DLD sector. The last of the deep layers are always the loss function when during the training. Okay. So intermediate layers parameters in every deep architectures have to be learned in this way. Okay. So using this method, you can get every layers DLD sector, the differentiation of the final loss functions respect to intermediate parameter sector. Okay. Okay. So because of that, this differentiability is very important. And again, you can think differentiability is roughly equivalent to learnability. Okay. So you have to get this DLD sector to update the parameter sector. For calculating this for every layer had to have these two terms, the differentiation of the output with respect to the input of that layer and differentiation of the output with respect to that parameter sector. Okay. If they can define this in the backward, you can calculate this for every layer using the chain rule. And if you can calculate this, then from the old parameter, you can calculate new parameters. And the parameters are getting wiser, seeing as more data comes during the training. Okay. So this is very important actually in deep learning. So are you guys following this indeed? Okay. So any differentiable layers could be located in between this RGB image and also the semantic label. But this kind of CNN architectures are frequently used when classifying the images. Okay, but that is because this convolution operation, which is the main operation in CNN, is differentiable. Okay, if you can get these two easily when when function f is constituted with this kind of plus, minus, addition, multiplication and division operations. Every polynomials are differentiable. Are you agree with this? Right? So if you constitute the function f with these four operations, that that function is differentiable with respect to their parameters and also their input. Okay. And CNN, the convolution operation, I will explain that later. This convolution operation is, composed of these 4 operations. So they are differentiable. In other words, they can easily calculate these 2 gradient values. Okay, so they can be used for training the larger networks. So they can be used to constitute the deep architectures. Okay. So from now on, I will show you what exactly is this convolution operation is. Okay, so this is the image. This is the 5 by 5 size image. In practice, this image, their dimension is a lot larger than this. Normally, we use this type of image, or even larger. We can use this dimensional images. So, and also in high definition TV, we use these dimensional images. Okay, so normally images are a lot larger than this, but I will show you some toy example actually when the image size is 5 by 5. And also there should be some filter corner for the convolution. So I explained that convolution is same as the filtering operation we normally say. Okay, so this filter corner is used, and when this filter corner is changed, the transformed output becomes different. Their characteristics becomes different. For example, when filter corner is having the 1 value for every filter, that is blur filter, as I mentioned in previous lecture. Okay, so I will again explain that. So, but before that, I have to explain what exactly the convolution operation does here. So this is the image, 5 by 5 image, and this is the filter corner with the 3 by 3 size. And what they do is, they first locate this filter on this part, the left topmost of the image, and we multiply every element like this and add them all. And the value becomes the left top pixel value. Okay. And then we shift the filter corner by 1 pixel right, and then do the same thing and calculate the output again. Okay. And we shift the window again here and do the same thing to calculate the last output in the top row. And then we shift this and get my window here, okay? And do the same thing to output the new output here. And do it iteratively. We get window here, window here, window here, until we meet the right bottom pixels, okay? And then we can get the output images like this, okay? And you can see their actual operation is composed of plus and multiplication, okay? So their output features are, if you define it as y, is differentiable to their input. And also we normally think to learn this filter corner for this convolution operation. So the intermediate filter corners are also differentiable respect to, this final output is also differentiable to this filter corner coefficient sector. Okay, so this convolution is because of that differentiable operation and can be used in between the deep learning layers. Okay. And this is the image blurring. So if you locate this 3x3 filter on this image and do multiplication of the pixels and filter coefficients, and by doing addition, get one pixel value here, and do it for every pixels, then these individual pixels are averaged by their neighbors, okay? So because of that, the images are getting blurred, okay? And if you change these coefficients of the filter, then the characteristic of your images, how to transform via these convolution operations are changing, okay? So somehow, by using convolutions and by learning the filter kernels of the CNNs, I mean, in the convolutional layers, we somehow learn how to transform the images. Okay. So yeah. Okay. And this is some hyperparameters of the convolutional operation. You have to use this kind of tricks. This is kind of trick to fit some dimensions, because I mean, in here, in CNN, you have to somehow, this is a 256 by 256 dimensional image. And by applying convolutions, somehow your images are getting smaller. And after a few rounds of applying the convolutions, the images becomes very small. And after that, you have to transform it to one-dimensional vector here. And you have to also transform this one-dimensional vector. And at the last layer, you will get the, d-dimensional vector. And this d-dimensional vector actually coincides to the number of classes. I mean, here the application is image classification. In image classification, you have to classify this image into multiple classes, okay? And let's assume there are D classes, then this output dimension of the CNN network should coincide with that D dimension. So at the last layer, you will get the probability for these D classes, okay? Are you guys following this? Okay. I mean, then you have to somehow manage how much you will reduce the dimension of the image, the original image size, okay? And for that, you have some tricks. But before that, you may see that when applying this convolution operation, applying this 3x3 filter corners on this 5x5 sized image, you will get this 3x3 sized output image, okay? There is some rule for how to say, for example, if you enlarge the filter corner size by 4x4, then initially there would be the 4x4 filter will be applied like this. And next, the filter will be applied like this. And then it would be applied like this. And it would be applied like this, okay? Then the output size would be just 2x2, okay? So depending on the size of the filter corner and the size of the image, the output image size would be decided, okay? So it is somehow hard to control. I mean, When this image size and filter corner size is fixed, there's no other way to control the output size. So there's some tricks prepared like this. So I mean, if you want to get a larger size of the image from the same size input image, given this same corner size and the same input image, if you want to somehow enlarge the output size, the simple scheme you can apply is the zero padding. Okay, what zero padding does is surrounding the original image with the zero values. Okay. So by doing the zero padding, you can get actually 7 by 7 dimensional image, having zeros around the original image. Okay. And if you do the same convolution with the filter corner size 3 by 3, then you can get this dimensional output. This is because it starts from here. Previously, without zero padding, it starts from here, and it stops in the rightmost here. But now it starts from here and can do convolutions for these values. So actually, these pixels are obtained from here and here. Okay. So zero padding is the easy way to somehow maintaining the original image size. Without zero padding, you can actually get a smaller sized output from the same dimensional image. Okay, but if you want to keep the output image size as the input image size, then you can use the zero padding. Okay. So this is kind of engineering trick to, control the size of the output size. Okay. Okay. And this number of paddings are necessary to keep the original image's size. Okay. When corner size becomes larger, the zero padding, their numbers should be become larger. So K is this dimension, the corner size. When corner size is 5, then 2 zero paddings are required to keep the output size same as the input size. Okay. Does that make sense? And another important hyperparameters are stride. Okay. Stride is how much shift the window, the corner window. So here, we just shifted by 1 pixels previously, okay? That is actually the default value for stride is 1. Because of that, we shift the window by 1 pixels. Okay. But if we use stride as 2, then we shift it by 2 pixels. Okay. Are you showing this animation? By 2 pixels, we shift when the stride is 2. So this output, their width becomes halved. Okay. When we use stride 2, then the width of the output becomes halved. And if you use stride 3, then it becomes 1/3 of the original image. Okay. So somehow we need to, in the CNN architecture, we need to decrease the 2D signal to make it eventually to one-dimensional vector that represent the class probability. So because of that, we tend to reduce the 2D image signals, okay? And actually using stride, this is the easy way to reduce the dimension of the input signal, okay? So using stride 2, you can easily get the halved image. And this is actually the convolution operation in, this is some operation introduced in signal processing field. So in image processing, which processes the image signal, this convolution was the main operation for, especially for the filter operation. So as you see, they can be used for blurring in this example, and also it can also transform images in multiple ways depending on the filter kernel values. So this is the 2D convolution, which is frequently used in image processing domain. But this is the basic for the convolutional layer in CNN, but convolutional layer in CNN is doing a few more things than this, okay? So this is, I draw this as the input image, and this is the filter kernel. So this is the blue one is the image, and orange, that's denoting the filter, and this is denoting the output. So this is input again, this is filter kernel, and this is the output. So in convolutional layer, one layer of convolutional layer, it involves multiple convolution operations. So I denoted I1, I2, and I3 here, okay? So this is denoting the 3 channels of input image. So this is denoting that the input is composed of 3 channels, okay? From that, we will get n-dimensional output. And actually n channels of output. And when doing that, what they do is they apply. This is showing the way to get the first output channel. For getting the first output channel, what they do is they apply 3 different filter kernels on each input channel and get O11, O12, and O13, okay? So the first index is denoting they will be used for first output channel. And this second index, they are denoting the input index, okay? Input channel index. Okay. When after calculating this O11, O12, and O13 by applying 3 different filter kernels on the input channel, what they do is they add them. Add these 3 channels to get first output channel. Okay. Are you guys follow this? So applying this filter kernel, as I mentioned, in this way, they get this output, first output. And by applying this another filter kernel on the second channel of the image, they get this. And applying this third filter kernel on this, they get this third channel for output channel 1. And they multiply, they add all of this response to get this. And this is the first channel, first output channel. And here you can see the indexes are now changed to, and this is again same as this 1, 2, 3. So this is obtained from here, and this is another filter corner to this one. This is another different filter corner, and this is another by applying another different corner to second input channel. They can obtain the second output channel for second second channel for second output channel. It's very complicated, and you have to calculate this by applying another filter corner, and by adding this, you can get O2, the second output channel. And again, doing the same, you can get a third output channel. And by doing this n times, you can get n output channel. So from the three input channel, you can get n output channel. N could be less than 3 or equal to 3 or larger than 3. You can design it by yourself. Okay. Anyways, you can adjust the the channel number n. Anyways, by using this n, you can get n output channel from these 3 input channels. This is the convolutional layers. I mean, you have to use this number of corners. If you use 3 by 3 filter corner, then you need to number of input multiplied by number of output channel, number of parameters for this filter. Okay, and actually this is our parameter sector to be learned during the training. Okay. So are you guys following this? Okay. And the other part, I will maybe restart it from this Wednesday. But the more important thing is, as you see here, this convolution operation is composed of only addition and multiplication. And also after that, when combining this channel image, you also have to use this addition. So your filter corners are differentiable based on, let's say this is as the output y, then, and also this, we will call this as the sector, then you can get this because their every operation here are differentiable, okay? And also, this is, let's say this is the x, then also we can get dy dx easily, okay? Because they are polynomials, okay? And this is another main modules for CNN, but I will actually explain it from maybe this Wednesday, okay? Okay, let's finish here for today. Let's finish here and see you at this Wednesday. Okay, thank you.